再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。
Ladies and gentlemen, this is Alice from Beijing. I can act talks, connect the world and the universe. Now today is a big day because this is the fifth time we have I can act talks online. We like this talk and I heard all the positive feedback from all over the world. Everyone says that they enjoy the talks very much. So this week we continue, for this excellent talks. So what do we have for this week? We have something new. Everyone can see that now on this stage, at this part, we have one new logo. This new logo is very special because this new logo is our new partner and my home school is Peking University. Now Peking University started a new program. It was X Lessons and PKU. The full name for this is PKU Global Open Talks. So it will be, ICANX Talks partners and to get all these, talks online and to help to organize all these talks. PKU Global Open Talks is one big, talks series because it will cover not only technology, all other talks too. So all this will start, right away. And the idea for this talk is study online, study from this. And this special time period, everyone knows that we have to do this. And it's a great opportunity for everyone to share all your knowledgements on the line. So this will be a big benefit for everyone in the whole world. You can learn more things from all these super speakers, super scientists, and super artists on this X License and Peking University. I'm so happy that we are together. And ICANX Talks will be one part of X License and PKU. And all the speakers will be, promoted by, X License and PKU too. So this is our great partner joined this week. So that's a great thing. Welcome X License and PKU. And we also have one more thing, to share this week. This week will be, very officially we start this new kind of event in the ICANX Talks. We dare between two speakers, we will have one new, things to do as a dialogue. So the dialogue is for this week, the theme is for micro nanoscience and technology, because we invited these speakers. They are all super scientists in micro nanoscience and technology. They did a wonderful job. And from bottom to space. What that means? It means they do the science from very bottom, from physics, in details in the bottom, and the application go up to the sky, even more than sky, go to the space. We have one speaker, Jürgen Brugger, his, results, his achievements was already go to the space. We will share that story and the dialogue part. So everyone will enjoy this. Every people, audience on this, ICANX talks, please stay with us. During between we have this dialogue, we will share all this, micro nanoscience and the technology from bottom to space, the background, and all these very nice stories with the scientists. You can hear that. And to dialogue and discuss with the scientists and this part. So without further ado, I know everyone here is really excited for one people's talks. But before that, I have two things to share with you as you can get more friends to jump in. We have Twitter, ICANX Talks online, so you can get all the latest information by this Twitter. We have YouTube. We put the ICANX Talks, X Talks videos online for replay. You can easily to find all these videos on YouTube by you search for the ICANX Talks. So if you use Google, you just search ICANX Talks. You can get all this information. And today we also get this online survey because we want to give you more, great service, to improve all these surveys and to get more information to you. So if you can feedback all this online service, that would be highly appreciated. So please do that, plenty of time for you to do. So without further ado, let's go to the first talk. Every week we're looking for the superstar, super scientist. Today is the most shining star coming in, Professor Zhigang Suo. He's from Harvard University. He done a lot of nice works, and today he's going to talk his latest results on the ions, electrons, and ionotronics. Look at all these words. You will see that which kind of big, magic here. It can, get all these ions and the electrons to talk together to make some new devices. And all these new devices, it's like magic. I leave the stage to Professor Suo. You will hear his talk and his excellent talk. So the word is yours. Professor Suo, welcome. And please share your screen.
Hey, Alice, thank you.
Yeah, great, here comes.
Let's see. So, am I sharing my screen now?
Yes.
Terrific. Hi, everyone. Thank you so much for coming. So, the talk today, let's see, let me get myself ready. All right. So, the talk today is ions, electrons, and ionotronics. My name is Zhigang Suo. I work at Harvard University. So let's see. Now, this painting, of course, is very famous. Let me get rid of this. So now, in the world, many people are, at least for a very long time, this is a belief how life was created. A soft machine, which is a man and a woman, created by something. So now, of course, this picture has been fundamentally changed about 200 or 300 years ago when this thing came into being, this machine. So we say life meets machine. The machine look sinister, but it is very useful for some other means. So this machine, life meets machine, has been going on for hundreds of years. Now there is one particular setup related to my talk today. is a particular way people life meets machine. This we call ionotronics. In this particular setup, if you go online, you'll try to look for this word, electrophysiology. What it means is you get a signal from brain, from your heart, from muscle, and nowadays put that signal, electrical signal, to computer or iPhone. So now, this is a human-machine interface. Human, we know, so electrical signal are conducted through ions, not electrons. Of course, our computers are conducting electrical signals through electrons. This setup is actually not new, has about 200 years of history. So this is the one setup of ionotronics. By ionotronics, we mean a circuit that contains both ions and electrons. Now, in this particular setup, you need to think about it. So even though there are electronic circuit in this machine, electrons actually does not enter human body. Similarly, ions are circulating in human body, but ions do not really come out into the wire, into the electrons. So the coupling between ionic circuit and electronic circuit is, they don't have chemical reaction. So this is one example, classical example, 200 years of history. Of course, this example has been evolving. For example, this computer is only available to human being for recent decades. Right? In old days, it was not computer, something else to collect signal. Right. Now, here is perhaps more familiar even to, how can I get rid of this? All right. So here, I apologize. There's something. All right. So here is another major example of ionotronics involve both ions and electrons for the function. This is, of course, electrochemistry. Classical electrochemistry, again, for more than 200 years of history. This is one example I use a fuel cell. The example came from Wikipedia. All right, so what you have is, what you want to achieve is to have a hydrogen molecule to a hydrogen atom molecule, and oxygen molecule react to form water. Now, this reaction generates a lot of energy. If you just let this happen, it's essentially an explosion, a lot of heat, light. It's not pleasant. However, you can do this more controlled way. This hydrogen molecule become two hydrogen atoms. This is an ion, proton, and two electrons at this interface. So this is one metal anode, and then this is called electrolyte, and this is called a cathode. Here, oxygen molecule comes in from the air and combine with these electrons and ions, and then it forms water. Now, what's interesting is happening. This was discovered, of course, almost 200 years. So instead of hydrogen molecules meeting oxygen molecules directly, so hydrogen molecules become hydrogen ions and electrons. Ions going through this electrolyte and electrons going through external circuit. If you have a light bulb, this electronic conductor, a light bulb will shine. So this is a primary, very successful example of ionotronic. The world batteries are also made this way. Batteries, of course, recently won Nobel Prize, right? Now, and here's another example. It's a more relatively recent. It started in 1970s. It's called biosensing. What's involved is you have a piece of semiconductor, there's a silicon. What you want to do is detect molecules or ions in the solution. It could be a human body or just a drop of solution. So let's say there's some molecules in the solution, and this one molecule absorbed on the surface. There's a surface of oxide. So it changed the state of the surface, and that will change the conductivity of a channel in the semiconductor. So this will turn into the change in the current from drain to source. This, as we said, already 20, 30 years of history. So I have 3 examples. Now, you would ask, then what is new? So life has been meeting machine, electrons have been meeting ions. What's new? So if you ask me what's new, if I want to answer in one word, that's internet. Everything else really is not new. Human bodies are not new. Electrons are old, but internet is new. Especially our world people have already decided that internet will connect everything and everyone, people and things. So in recent decade, we have a cloud computing, and we just mentioned we can have physical, chemical, biological sensing. When data are collected, we can do machine learning. So this will have a profound change of society, more so than the printing of books and all these other ways for human communication. So leading to this is a mobile health and a neural recording. So if I begin to think about something, perhaps you don't need to learn from me. All you need to do is have a computer send that signal to your brain. So there's no 20, 30 years of learning anymore, possibly. So we need to have this computer brain interface. That's human being, right? This is a dream for human. God tell you something in the dream, you don't learn anything. You already understand. So, so the new God, of course, is the internet. Stretchable electronics, wearable electronics, implantable electronics, injectable electronics, soft robots, soft machines. This field is so chaotic, full of energy, lots of names. But the essential new thing really is just internet. The internet will change our life for the coming century. Will play out slowly. All right, so now that's what's new. The other thing is new. What I need to tell you about is a material. We know matter of life, material of life, much better in recent decades. Today, I will focus on a class of material called hydrogels. So this hydrogel really is just a lot of water. Hydro means a lot of water. Gel means you have a polymer network. So gel is just hydrogel, just water molecules and polymer network combined. Water molecules are liquid-like wetness, so there are other molecules can dissolve in water molecules. They can migrate, move around, and react. That sustains life. Polymer network is solid-like elasticity that enable large and reversible deformation. People are familiar with hydrogel life. So first of all, plants are hydrogel and animals are hydrogel. And of course, plants product, this is a tofu, and animal product, jello, so food are all hydrogels. So that's a matter of life. This is an ancient material, as old as people life itself. However, what's new really is a synthetic hydrogel. Synthetic hydrogel has a definitive birthday. So it started in 1960s, about my age. So it's a very young material. So there's a first paper, definitive paper published in 1960, and in 1961, you notice even the first paper, it's clearly, so there's called hydrophilic gel, means hydrogel for biological use. Their biological use is contact lens. Now people know a contact lens, that's a hydrogel. So in 1980s, there super absorbent diaper, ongoing are tissue replacement and tissue repair. This is ongoing. Now, so there is a dramatic difference or just a revolutionary happening made by a Chinese professor who works in Japan. Jianping Gong, she is our hero. So 2003, she published a paper called Tough Hydrogel. Now, this is ordinary hydrogel. This column is ordinary hydrogel. Ordinary hydrogel is like tofu. Here's a piece of hydrogel. You press it with a metal. A hydrogel fracture like tofu, and this is just hydrogel. And she discovered a hydrogel. This hydrogel, like a rubber, you compress it, it deforms enormously. When load is reformed, this hydrogel spring back. So we call it tough hydrogel. 2003, not too long ago, about 20 years ago, this is a definitive advance in our field. Since then, worldwide effort to improve this hydrogel, because if you look at a human being not a whole tofu. Our muscle, our heart, our cartilage are very different from our brain in terms of mechanical performance. So her work really get us started. So here's one example created by my group. We published in 2012. We're followers in this game. So, and it's kind of cute. At that point, it breaks some world record. Here, what you're looking at is a steel ball calling from the seating. I have a layer of hydrogel about a millimeter in thickness. You can see this hydrogel behave like a rubber. It has 90% water, but behave like a rubber. It doesn't like tofu anymore. So that was exciting. And then, so here, now this talk is not about the materials. I want to focus on device. I want to give you a little bit of intuition about how we created this material. So this material is created in the following way. I already mentioned that hydrogel has a polymer network and a lot of water. If you just make this hydrogel is not very tough. We have a number to measure this toughness, 100. It doesn't matter how we measure it, 100. It's not very tough. So some natural material, in this case, seaweed, is also not very tough. It's fragile like tofu. The toughness is 10. When we combine these two materials together at a molecular scale, that toughness become 9,000, look like a rubber now, natural rubber. So this is a hybrid gel. It turns out many hybrid gels have this characteristics. Now the worldwide web, hundreds of formulation. We call this a black magic, black algebra, black. Brittle material plus brittle material and equal to tough. Today, I don't have time to tell you the physics of this magic. You can check our paper. I want to go to device quickly. Now, the other major advance was made. I just highlight a few milestones. This is done by a group at MIT, Professor Xuanhe Zhao, just a superstar in the field. 2016, he discovered that you can use a similar means to bond hydrogel, tough gel, to any substrate, could be glass, could be a piece of metal, could be plastic. So his method is you need to have some strong bonding between gel and substrate, and you also need to put some dissipation mechanism inside the material. The toughness can be as tough as the material itself. He calls it tough adhesion milestone. This is something people wanted to do for decades. Adhere hydrogel to something else. He achieved this in 2016. Right. So another recent milestone. This is our version. So together with a colleague David Mooney and Yusuf Lasik and many students, we achieved this tough hydrogel to bonding of living tissue. So this is a heart from a pig. So, and you can see this is a hydrogel. There's a transparent thing is our hydrogel, tough hydrogel. And then we adhere this hydrogel to heart with a lot of blood. And you can see how tough it is. I already told you that the hydrogel itself is very tough, like rubber. So you can see it's being stretched, and adhesion still remains. So this adhesion beyond 1,000 joule per meter squared, very tough. Before this, the adhesion energy between tissue and the hydrogel is about 10. So, and this, of course, is important for wound closure, doing surgery, and drug delivery. A lot of people are pursuing this now. Recent advance, very recent, just a recent year or two, we made another achievement. So the tough hydrogel all has a large dissipation, meaning it dissipates a lot of energy because you want to have a high toughness. Dissipating a lot of energy is not very good. So they're here, dissipating a lot of energy. So this is Jianping Gong's tough gel is here, dissipate a lot of energy, achieve toughness. And this is our tough gel is here. And many elastomer, rubber-like materials here. But what people really want is very low hysteresis, but very high toughness. Recently, we achieved this. This is our recent material red. Achieve a very low hysteresis. Energy dissipation in normal operation is very low, very elastic material, elastic and tough. We call this class of material elastic dissipator. Again, today, I'm not going to tell you detailed physics and chemistry to realize this. This belongs to another talk. So that's my short overview of major advances in life-like materials, this hydrogel. So around that time, we were doing this, people ask us, okay, so what, Zhigang Suo, you made these tough material spectacular. What can you do to change people's life? So at that time, I had a tentative answer. So at time, our group was also pursuing another thing. This is a paper published by another group in 2000. The paper is called artificial muscle. So what a muscle needs to do is the following, the function of muscle. Function of muscle is you get a signal from brain. Brain says you need to move, and the muscle moves. So that's a function of muscle. Very simple, but extraordinarily difficult to mimic. So this group, this engineering group, remarkable group, published this paper 2000 as, we don't need to mimic the anatomy. Anatomy is hard, chemistry, complicated, biology, complicated. Let's mimic the function. All I need to do is have a brain mimicked by electrical voltage. This is my brain. Just apply a voltage and please move, and this thing move. So all I need to do is follow it, right? So apply a voltage, and the voltage causes the motion of this material. So that's my artificial muscle. So the physics is relatively simple. all I need to do is have a soft insulator, like a rubber-like material. It's an insulator. Electrical current cannot go through this material. And I apply a voltage. So I put a positive charge, positive Q on the top, and a negative charge, negative Q on the bottom. They attract each other. The charge cannot go through the material. It's insulated. And this causes deformation. Wonderful. It actually works. They achieve strain greater 100% and very fast, on the order of 1,000 hertz, something like that. So that was the material. And we also know, they already demonstrated, this need to, for this thing to work, you need to have a high voltage, maybe 10,000, 10 to 4th volt. And we understand the physics of this. There's a various way you can reduce this to on the order 10 volt. It's possible, but the initial demonstration has a high voltage. That was very exciting. My group, the worldwide, many groups were doing this, improving this. Now, so at that time, we had an idea. The idea was following. This technology had a dark side, black side. Now, in order to spread charge on an insulator surface, you need to have a conductor. You cannot use metal, such as a copper. If you use copper, the copper will prevent the motion, deformation of this material. So what people use is carbon grease. So black carbon, put in oil, and you drip this carbon grease on top. And this is a conducting, and it's a grease, a liquid-like. It can flow so that you can have a material deformation. This is dark. The insulator itself, is this transparent, beautiful material. And this dark thing is so ugly and so dirty, terrible thing to do. So we say, oh, how about we put hydrogel on top and the bottom of this elastomer? That was our idea. So I had two postdocs at that time. This is a Korean fellow, Zhigang Suo, and then Austrian fellow. Both are postdoc in my group. So these two guys made this material hands-on faces. So the material in front of them is this transparent hydrogel. And you can appreciate this hydrogel is transparent. And it's also stretchable, highly stretchable, rubber-like material. Furthermore, this hydrogel, we already said, has a huge amount of water. 90% of water can dissolve ions. So it's a conductor. So the title of our paper is not called hydrogel. It's a paper about hydrogel, but we call hydrogel stretchable, transparent, ionic conductor. People really love it. So we say, how about we use this material to make device? That was our beginning thought. So this material, let me show you. This material, see, we have artificial heart now. You apply a voltage, and this voltage can cause the mechanical motion. So this is 1 hertz. So when voltage off, you have a small heart, and when voltage on, you have a bigger heart. And this heart is fully transparent. All the color is just transparent to all color. The structure is very simple. We just said there is an insulator in the middle. It's a thin sheet about, let's say, 0.1 millimeter in thickness. And we have a hydrogel plus a table salt. So this is a hydrogel, one hydrogel, another hydrogel. Here is a piece of metal coming from the computer, let's say. Apply a voltage relative to the ground. And the electronic current comes to this interface. Then I have ionic charge. This ionic charge induces ionic charge here. This ionic charge, positive and negative, attract each other. They have deformation. Voila, I have a heart. So again, we mimic function. We do not mimic anatomy. The real muscle doesn't do this. We're artificial heart. Right. So that was the initial. So let me show you how it looks like. So here's our device. We have a transparent dielectric elastomer, and then we have a hydrogel, which is also transparent. We have a rigid frame. We apply voltage to the hydrogel top and bottom, and you can see when we apply sinusoidal voltage, the voltage is applied here, sinusoidal voltage, you can see I can cause motion. And as the frequency of voltage go up, the frequency of, I can see the motion. So this is a very beautiful classical mechanical experiments. The frequency is going up, the amplitude going smaller, amplitude of vibration. Also, you can see the wave pattern become fine. So at this point, you cannot see very much motion anymore. But I hope you hear the sound. You hear the sound. Now I turn voltage into sound. That's spectacular. That's spectacular. So then we made a transparent loudspeaker. The whole loudspeaker is just this piece of beautiful transparent hydrogel. So this is a transparent hydrogel. I use a computer, or we use computer to send electrical signal. This electrical signal apply to this transparent piece of hydrogel. The hydrogel doing some little vibration, send out a song. That's beautiful music. So at that time, we want to give a name to this. It's no longer electronic music. It's ionic music. The beautiful thing is iTune. We call it iTune. Totally beautiful. Right. So I want to give you some physical intuition about how it works at the level of electrons and ions. So here is a piece of our hydrogel. We call it electrolyte. It's a traditional name of ionic conductor. It is stretchable. This material is stretchable, and we said it's transparent. Now let's say if you have a metal in contact with this hydrogel, this metal probably come from a computer. So this metal apply a voltage. What voltage does is send electron to this place or take electron away. But electrons cannot cross this interface. You have ion cannot cross this interface. So they have a positive and a negative charge. It's called electrical double layer. So electrical double layer, if you blow up, it looks like this. You have electronic charge on one side called electrode and ionic charge on the other side. So this almost like a capacitor. You cannot have a current through this interface, but you can change voltage. If voltage becomes too high, about 1 volt, you cause breakdown, you cause chemical reaction. But as long as your voltage is within 1 volt, you're safe, roughly. So this is one surface. On is another surface, we know we have a dielectric. So this is a dielectric. Of course, charge does not go through. I have ionic charge on this side, maybe electronic charge on this side, and you can cause deformation, can cause things on this side. So these are the basic physics, how ions and electrons move. So now here is our beautiful loudspeaker, and this is so we have a hydrogel electrode on top and the bottom, And then we have transparent elastomer. We have a rigid plastic frame. Then we apply voltage onto the hydrogel on top and bottom, and this thing start to move. The motion is minute, but it's good for generating sound. That's how it works. But remember, the voltage I told you I need to apply to cause motion of an elastomer need to be 10,000 volt. Enormous voltage. But water, hydrogel, can only sustain voltage about 1 volt as metal. This is a piece of metal and a hydrogel interface. On this interface, I can only sustain about 1 volt. But for this elastomer, we need to apply 10,000 volts. How can this work? So in the beginning, we were so worried that we're going to produce water or produce split water into hydrogen and oxygen gas. I keep asking my postdoc, please look for gas bubbles. Please look at the gas bubbles. And they told me, Zhigang, come to the lab. We cannot find a lab, cannot find bubbles. You find bubbles for us. There is no bubble. So eventually we understood the physics. And we were so excited what's happening. Physics is like this. So if you have a circuit, so the middle elastomer, this piece, is just like a regular capacitor. This is the elastomer, capacitor C. And this EDL, electrical double layer, is another capacitor. So forget about it. This hydrogel is a hydrogel. This piece of hydrogel is like a conductor. So now we have this capacitor and another EDL at the bottom. Another capacitor, they're in series. When capacitor in series, voltage drop across capacitor, voltage drop on across EDL and across elastomer is inversely proportional to the capacitance of these two capacitors. And we also know the capacitance is inversely proportional to the thickness of capacitor. Now, this capacitor thickness is about a nanometer, or it's just a EDL, right? Electrical doubling, nanometer in thickness. And this elastomer, I told you, is about a millimeter. So this difference is enormous, at least 1 million time difference. Of course, then voltage difference is 1 million times. So I only need to drop tiny voltage across the interface, will not cause electrolysis. There's no chemical reaction here. But I can drop enormous voltage across this dielectric. So this is how it works. That's wonderful. And then, of course, once we have a loudspeaker, we also can use loudspeaker to create active noise cancellation. So we had a vision that this is your window, and once you install this, the outside will have no noise, maybe very good in noisy city or car. So here's another early experiment published in an extremely good journal called Extreme Mechanics Letters. So what we want to do is have an artificial axon. So the axon, the real axon, its function is here's your brain, here is your hand, let's say, and your brain said hand does something. There is electrical signal going to your hand, and your hand does something. The distance is fairly long, on the order of meter, right? So now what we want to mimic this. Now in the real axon, so there is a salty water outside axon. That's our body fluid. Inside axon, there are also salty water with a lot of salt in it. But there is an interface. This interface is a fatty tissue, like a dielectric. It's called a myelin sheath, like dielectric. We say, aha, we can simulate this with our thing. So this myelin sheath, we simulate with elastomer. It's a hydrophobic fatty material, elastomer in the middle, body fluid we simulated with hydrogel, inside body fluid, inside axon, use hydrogel. So here's my brain, just apply voltage. And we apply voltage, see if I can get a signal at long distance. That's our artificial axon. Does it work? It works spectacularly well. Here is a demo. So here is artificial axon. And what we do is connect this axon to a cell phone. Cell phone is our brain. The cell phone apply a little voltage. And then we play music here. So music is a voltage signal going through this, and then play music. And this voltage signal is also passing from this conductor connected to this electronic display to show this voltage signal. Now, this beautiful artificial axon is transparent. We said our thing is transparent, and it's a highly stretchable. These are two students in the group. Chang Hui is already professor at STICs in Shenzhen University, and Bao Hongchen is still PhD student at Harvard. These are the professors working with us. The actual work was done in Xi'an University. And you can see how stretchable. So here's one experiment you can do to yourself now. You can listen to the sound quality as these two students stretch this elastomer. Can you detect any sound change as they stretch? I cannot detect anything. So it means our sound, the signal transduction through this line is insensitive to large stretch. This stretch is 6, 7, eventually they will stretch 8 times. Now, finally, after you break this conductor, of course, music stops. So this works really well. And so now we analyze this. So we try to understand, get some physical intuition about this. Essentially, if you make signal, the brain signal or the voltage made by the cell phone, this signal needs to transmit over long distance to this loudspeaker or to your hand. The question you need to ask is how fast the signal, voltage signal, can transmit over long distance. We all know the ions need to diffuse, right? But ion diffuse in water, in gel, is very slow over long distance. How slow? The diffusivity of ion in water is 10 to minus 9 of this unit, extraordinarily small. But what we're interested in is voltage signal, not matter, not ion diffuse. How voltage signal diffuse? So we have a little model. This voltage diffusivity is 10 to positive 7. There's a 16 orders of magnitude difference between signal transduction diffusivity and ion diffusivity. We were so delighted. That's why signal diffuse so fast. Anyway, so that was a result and our little measurement. So the conclusion is we can do better than real axon, our artificial axon. We can transmit a signal, megahertz signal over meter, no problem. Okay, so and so I'll skip. Let me just describe this. So here is a little demo. 2 LED we send this signal, electrical voltage, and we have two LED here. We send electrical current through this hydrogel. Now, this is an important point, principle we discovered. The LED we all know operate through electrons, not ions. This is not ionic LED, just electronic LED, right? Now, how does ion send this signal, ion signal, to electron? That's interesting because it's an ion, electron, ion will be stopped as interface between metal and hydrogel. Now, our design, what we call a rocking chair design. We have two LEDs. They operate in anti-parallel. We don't really need to have electrons going through this hydrogel. Here is, let's say this is a hydrogel. So all you need to do is apply voltage. So what voltage happens is you can charge up one LED, make one LED shine, and then this LED will feed electron to another LED. And then the other time you reverse your voltage, this LED will feed electron to this. So they feed to each other. We call it a rocking chair design. So let's see it again. So your voltage is low, frequency is low. You can see one shine at the same time, one shine at one time. But you increase the frequency. Gradually, you can see the light appear to human eye become steady. So you can use hydrogel to operate electronic device. That was a principle to us. And then we actually invented a device. So here's a device we call ionotronic luminescence. You can see when we apply voltage, you can have electroluminescence. The device principle is like this. So here we have a phosphor in the middle. The phosphor is electronic material. It is just a ceramic particle. Ceramic particle here is a lens bar about 10 micrometer in size. These particles, 10 micron in size. These particles, once you inject electron into particle, the particle is known to meet with a hole and generate light. So this is called a phosphor. Now, what we do is having this phosphor ceramic particle glued in between two elastomer layer. And then we apply voltage through hydrogel. We do not inject electron, right? It's ionic and there's an insulator. But we can apply voltage. As long as the voltage is sinusoidal, essentially the particle can generate an electron. Electron meet the hole because the particle itself can generate electron. You don't need to inject electron. As a result, once you have a sinusoidal voltage, you can really shine light. So this become ionotronic device. So the beauty of this device is because our hydrogel and everything is transparent and everything is stretchable. So we have a small heart can generate light, and you can stretch this to this enormous heart. It can still generate light with the same intensity. There's no degradation of intensity. So it's a stretchable. So we published this work in 2016, and another group is a friend. We actually know this guy, but we were totally independent, published almost identical work. Same year, just almost exactly the same time. So it's a very exciting, good idea generated by two separate groups. All right. So here's another demo. Let's see. What happens is there is so if we have hydrogel, right? This hydrogel has a field concentration near the edge. So there's a beautiful device at the edge. It can shine light if you have a luminescent particle at this point. So this gives us another idea. You can apply ordinary voltage, but through field concentration you can generate light at a selected spot. So yeah, this again published in Extreme Mechanics Letters. So here is another idea. So you focus on this device here, and you can see when you apply voltage, you can make this thing transparent and also shut off. This is what we call ionotronic liquid crystal. The idea is very simple. If you have a liquid crystal in the middle, hydrogel on the top and the bottom, you apply voltage, you can turn liquid crystal from the random state to aligned state. In random state, it blocks the light, and in aligned state, it transmits light. Here we use the property of a hydrogel, two properties. One is hydrogel can apply a voltage. Two, the hydrogel is transparent, so the light can go through the liquid crystal. Furthermore, the whole device now become stretchable. Now we have a stretchable liquid crystal display. Now your display can be stretchable, highly stretchable display. All right, that's exciting. Here's another example. This is a Christoph. Remember, he was a postdoc in the group. Now he's a professor himself. Published another science paper, 2018. So he combined in gel, elastomer, and the liquid into a device with enormous actuation. Very exciting. So here is the work. Let me just turn on this work. So this is a pad, ionic pad. You attach this pad and then you can control something. So we call it ionic skin or ionic touchpad or iPad. This was the idea Zhigang Suo did when he was in my group. And then he became a professor himself and published his own paper. Similar idea, but now it's spectacular. Look beautiful. So it's an iPad, ionic touchpad. So of course, this idea has enormous potential. You can put ionic sensors, we call it ionic skin. A lot of people develop an electronic skin because the people are ionic. If you develop a skin, why not just make it ionic? So then everything is simpler. So we put ionic skin on robots and on people's skin. This is a stick-on large string sensor for soft robots. This is another interesting thing. We just published again in Extreme Mechanical Letters because this is a soft sensor, very soft. We can sense the bite of the teeth because the teeth is irregular. In the past, the sensor is rigid, very difficult to conform the irregular shape. Irregular shape of the teeth. But with a soft sensor, you can do this immediately. Furthermore, you can have one sensor for each teeth. Now you can use the same piece of soft material to collect the signal, multiple signal from all the teeth. This is very exciting. We talked to dentists. This paper, the initial demonstration just published. This seems to have a potential. But you can also imagine if this is a machine with a different shape, now you can sense a complicated machine the same way. That's very good. Now, this is an interesting, enormous number of people want to do this, just detect a neural signal, right? Here is, let's say, this is a neuron. Here's your computer. We use a hydrogel as an interface. So hydrogel is ionic, your neuron is ionic. So then ions can just seamless go through from hydrogel to neuron, and the hydrogel itself can induce electronic signal in your computer. So now the question is, how do you put a piece of hydrogel, which is soft, into brain? So let's say you have a mouse, have a soft brain, and you have a piece of soft gel you want to insert into soft gel and collect brain signals. So this is a voltage as a function of time. How do you do that? We had one idea that might be useful. We published again in Extreme Mechanics Letters. So what you do is you make this hydrogel frozen, 0 degrees C. It turns out the brain can tolerate 0 degrees C for a short time. And then because 0 degrees C is ice, is rigid, you can insert this into the brain. And then it melts, become hydrogel. Then you can really connect signal. So we're convinced, and this is in collaboration with colleagues at Zhejiang University. They're professional biologists. They convince us these signals that they can collect with this frozen gel is as good as the best metallic electrode you can collect. Same signal. So that's great. They can instead, in addition, they can detect when the mouse is sleeping and when a mouse is awake, the signal look different. They can do that. And when mouse is feared or gets excited, happy, they can detect all these signals. These were described in this paper. That was exciting. It's an application for us, but many people want to detect signal and influence people, right? Suppose, right, a Chinese government or actually US government want to persuade you, right, coronavirus is safe. Instead of using words, they use the computer. That will be more effective, right? People will believe this more readily. Good. So here's another piece of science we did. Let's see, maybe I don't have time for this piece of science. Let's skip this. Let's skip this piece of science. Let me just tell you the basic result. The basic result is found. This is enormous important in the future development. Now, we use rubber-like material. Rubber is because it's stretchable as an insulator. So this is a rubber-like elastomer, rubber-like material. Rubber-like material. So even for very hydrophobic rubber, doesn't like water. This is a permeation of water. Permeability is actually quite high, much higher than something like silica, silica and silicon nitride, all these inorganic material, and of course graphene. Why this is important? Because all the microelectronics need to be sealed against moisture. That's a standard seal. So microelectronics works because you have this inorganic seal. Now, just imagine you want to make anything stretchable. You cannot use this inorganic seal. You have to use organic seal, this elastomer seal. Elastomer seal just not good enough. There are just many orders magnitude difference in permeability. This is a fundamental limit. You need to design your device. So it's an intrinsic limit to bioelectronics. Not only permeation of water, also permeation of ion. So we say all the stretchable electronics now are naked. They do not have a clothes. In principle, they cannot last very long and do not work very well because the permeation of water and the permeation of ions through the elastomer. Time again to learn from biology. This will be a separate talk. And here's something else, material development in recent decades in chemistry. We borrowed from chemistry, something called ionic liquid. So this ionic liquid has no water in it. You just have a positive ion and negative ion. There is no other solvent. So they're just ion and ion. What we can do is use this ion, put this ion in a polymer network. This ion is called ionogel. Now, this ion is spectacular in one way. it doesn't evaporate anymore. So if you have a piece of tofu in the kitchen, if you left it for a week, it will dry out. But if you leave this ionogel, you can leave it for any number of years, it will never dry. And also, it can go to, it's non-volatile. It can have a large temperature range. If you make a hydrogel, the temperature range is between 0 and 100 degrees C. But if you make ionogel, the temperature window can be very large, much below 0 degrees C and much above 100 degrees C. So hopefully, now people are exploring for industrial applications. Very excited. We just published a paper this year with, this work was led by Ryan Hayward, our longtime collaborator. For decades, we've been collaborating from the University of our home state. So this is a material called ionoelastomer. Now this material is interesting. So one kind of gel, one kind of ions connect to a polymer. The other kind of ions become mobile. So this is almost like a semiconductor, ionic semiconductor. So this is a positive mobile ion. You can also have a negative mobile ion. So this is another, it's an N-type or P-type elastomer semiconductor. So now you can begin to imagine ionic semiconductor. And also, I don't have time to explain, there's a coming up paper just accepted recently to demonstrate this pair has a very large adhesion, high adhesion. And this adhesion can be tuned from a very small to very large by an application of voltage. Very excited about this. So, and this is a paper accepted yesterday. I just added the slide yesterday. We don't fully understand the mechanism yet, but with a lot of potential. We call it a stretchable electrode. So what happens is you can put a little particle in a polymer network. So this particle, what we did is a glass particle, nanoparticles. The particle as a joint is not very good. The particle is large compared to polymer network. So the particle cannot move around, but they can trap charges forever. This glass, silicon, can trap charge forever. So we inject charge into this material, into this bulk. So when you deform this material, elastomer, the charge just move around, not flow, just move around with the particle. So this effect called a electrode, it contains charge. But now this electrode can be largely deformed. And when you deform charge, of course, you influence anything nearby, just remotely electrical. So here's a little demo, which is quite interesting. So here's our material. You can see this material is transparent and move around. There's no touch with this material. And this material is electrically connected to this display. So when this material is moving, let's see this again, and we can get a signal. There's no contact. You can make this into any shape. It's transparent. Also the charge, you can have a pattern charge. So here's another demo. This demo is, let's say you stretch this again without contact, and you can see this non-contact electrical signal. You can do that. We're very excited about this, so lots of development. Now, this is my last technical demo. So fabrication. Now, it's a virtually open field. You really want to integrate soft materials. So the revolution in last half century is integrated circuits, where you integrate semiconductors and metals and plastics, dielectrics, But these are hard materials. Took decades to develop that technology. Now, if you want to integrate materials like a human being, or people like to talk about synthetic biology, then you need to integrate soft materials. Here we made a preliminary demo, just integrate elastomer and hydrogel. So elastomer is hydrophobic. Hydrogel is hydrophilic. Even that wasn't integrated before in the past. So now we have a way to integrate this material, and we just show it did very well. We demonstrate again this artificial axon demonstrate too. You can see the result is just spectacular. Here is our hydrogel, and its materials is so good we can use a hammer. While you hammer this electrical signal going through, you can still play with it. So this is better than artificial real axon, right? It can sustain high load. Again, this work was done in Xi'an Jiaotong University with Professor Jingda Tang. He is a young faculty, very, very creative, new star in the field. Okay, so now here's my concluding section. I want to thank Alice to create this wonderland. We're doing adventure in this wonderland. In this talk, I showed iMusic, iTunes, they're all enabled by Ionic, iPad, iSkin, iBot. So then Alice, of course, created this idea a long time ago. He called ICANX. I don't know what she had in mind. In my mind, it's called Eyes Can Do Everything. IX. So now in the talk, I didn't have a lot of time to describe even our own work. Much of our own work in this area is reviewed in a recent article. You can see this field developed so fast. It's already a little old now. But our website has all our recent papers. You should download. And I have almost zero time to describe other people's work. I just cited a list here, few recent review articles, not even original paper. This is a Chang group from Singapore, very energetic group. Now, this is Jianping Gong. Jianping Gong is a world leader of all of us developing soft material devices, materials. This is her latest review. Spectacular, it's just very well written. And my long-term collaborator at EPFL, this is her review. She is a world leader in doing this neural interface together with her biology colleague. And of course, to study charges in the material, the king of this field is Zhongli Wang. Nobody competes him. Here, I don't even bother to cite reviews. He has too many reviews, but everybody should watch I Can Talk. And this is Xuanhe Zhao, a huge star in the field from MIT. He is a young leader in developing mechanics of soft materials for lots of applications. Again, you cannot even have time to read his paper. Just watch this video. The video is extremely well produced. He is a world best speaker ever. Of course, John Rogers. John Rogers is an international leader, just a trailblazer for anything to do with stretchable electronics. He also has a video, EML webinar 2020. You can go online. Here's how to follow us. If you're in the rest of the world, you do Twitter. If you're in China, of course, Twitter is not available. I don't know why. WeChat. I'm also active on WeChat. So yeah, publishing papers are too slow. in this field. That's the end of my talk. Thank you very much.
Okay, thank you, Professor Suo. Wonderful talk. Ions can do everything. I like this. I can X. Yes, yeah. So, how many people listen to your talk? Can you guess? Imagine?
I have no idea.
You no idea? I tell you. Okay, 231,000.
Okay, that's good.
That's really interesting. Yeah, could you please, close the screen sharing? We can go to the question part.
Yeah.
Okay. Yeah. So we have a lot of audience, so they have many questions. We go directly to this. First is Tim Jeffney from University of Canterbury, New Zealand. Is there any special procedures required to achieve a good bond between VHB and hydrogel? Have any other materials for the dielectric been, investigated? Yeah, please.
Excellent question. So when we generated our first version of iTune, we just put hydrogel on top of a VHB. The adhesion was terrible. Sometimes because we need to apply cyclic voltage. When our voltage is at right frequency, the hydrogel downs off elastomer. We have a dancing hydrogel. The adhesion was so bad. We didn't know because we were not expert on adhesion at that time. It turns out people knew about that problem. Hydrogel adhesion elastomer or hydrogel adhesion to anything had been a problem for decades. For example, people want to adhere hydrogel to human tissues or hydrogel on medical instruments. These are all established technology for decades. People need to fake or doing something, one thing or another, no good solution. So then in 2016, Shenghe Zhao at MIT made a transformative advance. He said, he could, and publish a paper in Nature Materials, adhere hydrogel to anything. So, and we look at everything in his first paper. It was exciting. It immediately got attention. But we found two things he couldn't do. He did not demonstrate that paper. One thing relative to us is elastomer. The other thing demonstrated to us was important to us was tissue and elastomer. So we immediately published papers or in a little competition, a friendly competition with our friend. So it's very hard. Who's first in the second? He was definitely the first to demonstrate the possibility of hydrogel. The answer to your question is yes and yes. Now we can. This is a claim. I think Shenghe will agree with us. In the field now, we can adhere hydrogel to everything. So the game has moved on. There are even several review articles. If you go to the list I just gave at the end of my talk, it will be available on the YouTube and on Baidu, this video replay. Just take a look at this if that's your question. We have also just explored multiple dielectrics. The principle we demonstrated are generic. All dielectrics work. So far, we tested many. There's nothing that doesn't work. Really, it's a very exciting time. I think it's analogous to the time when in late 80s, when Bardeen and his friends discovered transistor with semiconductor. So materials is there, the physical principle was understood, but people had very little idea what could be made, right? There was no computer, right? And also people had no means to integrate these materials together. So that's an exciting time. So people had to start this TI, right? Textile instrument, not instrument. So this guy who started this integrated semiconductor and the metal and the plastic together, this guy also won Nobel Prize. Just put materials together, won Nobel Prize. There's no physics, right? I think this is our time now. It's our time, this time integrating soft material for integrating with people, biology, or integrate with plants, and also create new devices, not necessarily integrate people. That will be another half century's work. We're in the early days. Very exciting. But to your question 1.1, that's yes and yes with exclamation mark. No problem.
Okay, how nice to hear the story from you. Xuanhe is your student. You're so proud of him, and then now do things, together. So the second question is, like from a girl, he got his name was Cutie Lily. Can ionogels and the transistors made of solventless elastomers have been used to simulate the nervous system? Has there been any attempt?
I think yes, they can stimulate nervous system, but then it has a different physical characteristics because in ionoelastomer, only one species of ions are mobile. In nervous system, multiple species are mobile, right? So simulate, maybe it's alternative reality now. Has there been any attempt? So far as I know, there is no attempt. The field is wide open. Here's something, it's an exciting period. So somebody said a long time ago, a smarter person, smarter than me, said a long time ago, if you live in late 1920s, when quantum physics was newly formulated, you can be second-rate physicist and you can do first-rate physics because there's just so many opportunities. And the smart people don't have enough time to focus on new things. And also smart people are already doing other smart things. But for this ionotronic device, just so many opportunities in terms of material variety, in terms of device integration, in terms of fabrication, and in terms of also device configuration, and also in terms of application. You need to invent a new market. So another idea I learned in my own career is very interesting. So when I was young, my field was electronic packaging. That was my field, integrated materials. So I work with Intel, with IBM. Some of these people give me money. Some people give me materials. Some people give me ideas. So I go to their conferences. Some of my contributions, theoretical contributions mostly, integrated in their design code. I was very proud. At one conference, people say the next thing is not a computer, it's a cell phone. That was early 90s.
Wow.
Not cell phone, right? At that point, it's a cell phone. Come on, I don't even have time with my computer. Why do I need to have this poor computer, small screen? I don't have time for this. So I refuse to have cell phone. So when Steve Jobs put out this iPhone, 2007, I think.
Yeah, 2007.
My two sons were so excited. I was just indifferent. So what? It's just a small screen, poor quality, with slightly improved resolution. What I did not realize, he invented a new market. That market is the entire world. everyone. You have
okay, Professor Suo.
you
Yeah,
have
we
to
need
have,
to
you need to have the vision of a Steve Jobs in this field. Of course, the other thing you can do is if you don't have the vision of Steve Jobs, find somebody like Steve Jobs and work for him.
Okay, we follow you. You are both, a leading scientist. We follow you. Yeah, the third question is from Zhuoqing Yang, Shanghai Jiao Tong University. Professor Suo, your great and interesting talk. Now, have this transparent material been commercialized? What is challenging in the process for commercial applications?
Thank you very much.
To connect with.
Yes, transparent material. First of all, this is not one material, several classes of material. For example, elastomer. Many transparent elastomers are already commercialized by big company like 3M and many companies. Transparent elastomer serving as a dielectric, commercially available. You can buy online. For hydrogels, so far as I know, nobody are commercializing it yet, but many groups are worldwide can make transparent hydrogels. For example, what we do in the beginning when we couldn't make hydrogels ourselves, we just collaborate with another group in tissue engineering, in polymer group, ask them to make these hydrogels for us. So very easy. You are from Shanghai Jiao Tong University, you must be able to find collaborators. That's easier. Now for ionoelastomer, that's a little trickier. Not every group can make that. You need to find a group to explore that with you. So for stretchable electrodes, that's very new. But after we published that paper, many polymer groups should be able to make that easily. So the answer to your question is, I think this field is ready for commercialization. The barrier at this point, the barrier for entry is extraordinarily low.
Okay, great. So yeah, next question is pretty long. Thanks for your wonderful talk. Hao Bin from Peking University has the question. Since the hydrogel can be used as a good medium for artificial muscles, artificial actions, etc., can hydrogel really integrate it with human tissues and bones together? I think the hydrogel has enhanced advantage compared to other, kind of steel plates and hard devices implanted in the human body. Yeah.
Thank you very much for that question. So integrating hydrogel and the human body have already happened. For example, everybody's familiar example is contact lens. That's the integration of hydrogel with your eyes. Right? So with the bones, people already done that in cartilage replacement. Now the new opportunity is not only replace the tissue, but also enhance the functionality. For example, can you make some electrical measurement out of tissue using hydrogel and somehow send that tissue to the cell phone? And the cell phone, once you are sending cell phone into the cloud. So next time you have a disease, then your disease, that information will be in the cloud, not even report to the doctor, report to another computer. Then computer can study all the population. So your disease become a source of information to cure somebody else's disease. So we all cure each other through the cloud, right? So that's a vision. This vision probably will play out in next, if I'm optimistic, maybe next few decades, not maybe a century, but that will happen. The new God is the internet.
It is. Okay. Yeah, we came to the last questions here. As is Song from Peking University. Thank you for your wonderful talk. The ion hydrogel is amazing. In addition to the good conductivity performance, how about other capability of such materials like energy storage and biosensing? Sun Chun?
Right. So energy storage. For example, hydrogels have been used as an electrolyte in batteries because it's just an ionic conductor. It has some other characteristics. It has been used. I think it has enormous opportunities. For biosensing, again, it hasn't been used because, but the new opportunities are how about direct integration of people? And how about biosensing? We're talking about multiple different kind of species. How do you differentiate these species through single voltage measurement? Maybe you need to do some machine learning to differentiate the signals. These are in early days. So I'm firmly believe, because the human bodies are hydrogels, it's complex hydrogels. If we can differentiate signals, we can surely create a system can better do our job.
Okay, great. So, Professor Sir, thank you so much. I prepare a certification for you from ICANX tax, and this time is together with PKU's X license. So yeah, we connect the world and the universe by your wonderful talk, by your wonderful technology. I think now we connect with the future. Yeah. So thank you so much. That's for you. Yeah. I deliver this electrical version to you. Next time I met you, face to face, I will give you a hard copy.
Okay, thank you, Alice, and thank you for ICANX. So, incidentally, Alice, this is a wonderful wonderland you create, ICANX. I already heard you explain X. Never heard you explain ICAN. What's ICAN?
ICAN is an event I run for 13 years. It's the contest for the students, for they doing innovative, creative project and get on a contest. You will meet all my colleagues on ICAN at this stage at the dialogue with the Jürgen Brugger and awesome all my colleagues for ICAN. Yeah, we done that for 30 years. This is a wonderful time. That's a project for majority for the honor students. They doing creative project and put them, into a contest. That's it. Yeah. So we continue this, with a dialogue. So yeah, Jürgen and also awesome. Please turn on your camera. And now is our dialogue time. Yeah, we got everyone on the screen. Yeah. So awesome. Yes. Here we go. Get everyone here.